Okay. Good morning, students. Today is August 16th, and we are 2 weeks away from completing this semester. Today, we're going to go on with the last part of the calculation of shear stress in sections when we have more than one cell, right? That's one. And then we're going to go to the next topic in this chapter, which is about how to calculate secondary structures, okay? That's more or less the agenda. At the end, I will leave some minutes in order to answer questions if there are some questions about the next assignment, okay? So let's go on. Let's see, primary response. Okay. Can you see my full screen? Anybody? Can you see my full screen?
Yeah.
Okay, so this is what we are analyzing, right? It's a section which has more than one cell, right? In this case, this is a indeterminate, statically indeterminate case. That means that with one single relation, which comes from equilibrium, right? That was the principle that we apply in chapter 2, is not enough. By definition, a statically indeterminate system is the one that cannot be solved only using equilibrium. That means that we have to bring something else. And this something else is a simplification of the expression for the axial distortion of the section, right? So this is in general, the process that I explained, and I posted a video yesterday about it, okay? And the first thing that we have to do is that we have to remember that when we have a section with enough cuts, right? For example, we have a hatch. We know that at the edge of the hatch, the shear stress is null. From that point, we could go on and calculate the first moment. And with the first moment, we could evaluate the shear flow. With the shear flow, according to the thickness in every point of the sector, we could calculate eventually the shear stress. Okay? So if we do not have any of these hatches or cuts, what we can do is we can include these artificial cuts. If we include enough artificial cuts, we could calculate this Q1 or Q2 star. Okay? Q1 and Q2 star could be calculated because we know we have included enough cuts in our section so that we could, using the single relation that we have available, we could calculate the shear stress distribution. The problem is that when we put a cut, right, at the point where the integration closes, there is a distortion, axial distortion of the 2 points. What we have to do is we have to add, in this case, we call it Q1 and Q2. Q1 and Q2 are unknown shear flows. We assume them as uniform in each one of the cells. Okay, look at the sign, at the direction. Positive is shown here clockwise. Okay, and these are unknown. That means that if we combine the QIs with the stars, with the QIs with no star, combine it in each one of the cells, we can calculate the axial distortion in a closed path, and the result should be 0. And that's this expression that we are seeing here. Okay, that means that on the left-hand side, we consider this Q1, and in here, this is a common branch. Q2 is also acting, right? And on the right-hand side, we put the Q star that we know. That's the reason we put it on the right-hand side, because it's an independent term in this equation, right? This is Q1. I'm sorry, this is the integral for this integral in this. The other is the integral in the second. Okay, again, we know Q1 and Q2. I'm sorry, we do not know Q1 and Q2. On the right-hand side, this is known, and we could solve this, okay? This process, okay, we implemented in a computer program that we call Shear Stress Multiple Cell, okay, this program here. And we allow you to use it. But the thing is that you have to understand the process in order to prepare the data, okay? So here is the input data that you have to prepare. All this information has to be prepared in a file in the text format, okay? Text format, okay? The positions of each point that you employ in order to define the paths, okay? And the thicknesses must be in the same units, okay? You also have to specify the shear force, okay? So you specify force, you specify positions, and the ratio of these two will give you the shear stress resulting from this calculation, okay? Now, in general, in a section, we have to set up the section with a reference system. Example, let's suppose that we have, in your case, you have something like this, okay? And like this. You know, for some reason, I start. Okay. Now, in general, what we have to do is we can start by specifying a reference system. The easiest way is to put it in here. So on the right, this is Y, and vertically, this would be Z, right? So for every point, any point here, we have YI, ZI. Okay, so we have to specify several points in order to define each one of the paths, and each one of these paths will compose cells, okay? Remember that in the vertical elements, the variation of the shear stress is quadratic, okay? So you need more than 2 points in order to describe the variation in this area here. I usually tend to use at least 4, okay? So we have 4 points, and with 4 points, we could have a decent variation of the shear stress, okay? In the case of the horizontal elements, for example, deck or double bottom, with 2 elements is adequate, but usually I tend to use 1 intermediate in order to see the variation, okay? So that's that. What information do we need to include in this data file? First, it's always a good idea to include the name of the project. Okay, it's just a group of characters, a alphanumeric variable, up to 50 characters. I recommend you to try to describe your example with as many as characters as you can, okay? Then the shear force applied on the section, okay? If you have the shear force, well, you can use it here. If you do not know, my suggestion is that you could have, or you can use 1 newtons, right? That means that since this is a linear problem, if you have a different value, Q units, V units of force, what the results is going to be simply V, the number V of shear force, multiplied by any of the results that we are obtaining, because this is for unit shear force, okay? Then we have to include a number of branches and cells. So here, you have to take previously your section, and you have included the artificial not include. So, okay. Okay, so you have to include the artificial cuts, and then with these artificial cuts, you can define the number of branches. The number of cells is easy. In this case, it's 4. Now, comes for each branch, okay? For each branch, you have to include this information, okay? First, the number of points defining the branch, right? So, for example, in this case, let's suppose that this is a branch from here to here. I will have 6 points for the branch. Now, for each point, you have to define its number. For example, that would be my number 1, 2, and this will be the branch, the point 6 of this branch, okay? And then for each branch, you have to put Y and Z values as we have specified here, okay? And also the thickness, okay? If you specify the second, this branch, you specify the thickness here, and that is assumed to be constant from 0.1 to 0.2, okay? So if in your section, you include changes in thickness, that's something that have to be considered when you specify these points for the variation of, or the number of paths, or the number of points to define each path, okay? As we said before, it's recommended that you include the origin of the reference system in the center line. I usually tend to put it here, center line in the bottom, but you could put it any place you want. Then, for each cell, okay, you have to see here, you have already defined the branches, okay? So you have these little pieces of the intersection, that's 0.4. In 0.5, for each cell, you have to do 2 things. This is form each branch. And this is the neighboring cells, okay? So for each cell, in this case, you have 4 cells. For each cell, remember, this is super important that you include, that you remember that this is a positive sense, okay? So for each branch, for each cell, you have to form it. How do you form it? Taking from each branch, okay, the points which are contributing to form this cell, okay? We have to be careful because this is the positive direction of each cell. And each branch has been defined probably in different direction. So we have to include the sign, okay, with which each branch contributes to form the specific cell, okay? And then you have to remember that there are certain, for example, in this case, okay, this cell here has this wall in common with this cell here, but also the double bottom, okay, this common, in this case, double bottom is in common with the cell, this other cell here. So this cell here has 1 and 2 pieces of paths in common with these 2 cells, okay? This thing here, this cell here has in common with this piece, and with that, this little piece, which is the bottom part of the longitudinal bulkhead. Okay, so all of that has to be defined in this part here, okay? That's defining the neighboring cells, what you have in common. And then here, in the class notes, you have this example, right? So we include 2 cuts. So we have 1 branch, 2 and 3 branches. And of course, we have 1 cell here and another cell here. So all of this information has to be included in here. Okay, so in this case, this is the name. So we see that we have the beam and the depth. Okay, so from here to here, that's 20 meters. From here to here, it's 10 meters. Shear force that we include is 1 meter. Now, 1 Newton, I'm sorry. You see that here, I'm including the value of the shear force. And then immediately to the right, with a space here, there is a name of this variable, right? I always do that so that next time I need to use this program, I remember what this information is about. Okay, so in this case, this is the value of the shear force. Then we have to define the number of the branches and the number of the cells. So as we said here, we have 1, 2, 3 branches, and we have 2 cells. So it's cell 1 and cell 2. And then we go. This is the information for the first branch. Okay, so we have 13 points for the first branch. We start, this is Y, this is Z, and well, this makes no sense. This is the thickness from this, from point 1 to point 2. So we start at point 0 and 10. So basically we start here. And you see that Y decreases. So we go like this. And for all of these points, the Z value is constant. Then we go downwards. So Y is constant and Z decreases. And then we close up to here, very close to the center line, and that's this part here. Okay, so Z is 0, and you see that Y is increasing from -10 until 0. Okay, so even though maybe you said, okay, this point should be -0.001. Yeah, but we said equal to 0, and there's no problem with that. Okay? This is the information for the second branch. So we go from here until down here. And then we have the information for the third branch, which is something like this. And that's this information. We use 13 points. Okay, you see that we have 1, 2, 3, 4, 5 points from here to here. Then we have 1, 2, 3, 4, 5 points from here to here. In another 3 points, or 4 points, 1, 2, 3, 4, and 5 points from here to here. Okay, so we have a nice description, variation of the shear stress in each part. It is possible that we could reduce in this and in this some of these points, right? Because you know that in this area, in this sector, the distribution of shear stress is linear. And here is parabolic. So in this case, for example, 5 points is good enough. In this point, in this area, and in this area, probably 3 points would be enough. But if we include more points, then the integration which are developing internally will give you a better result. Okay? And now, here we have the last part of the information. Okay? This, okay, defines, okay, each cell with the branches. And this part here, for cell 1, defines this common, which is shared between cell 1 and cell 2, right? This is very important. This is the sign. This is a sign. So we see that the cell 1 is formed by first branch 2. You see that it goes in the same direction. So this is positive. And we use 5 points in the branch 2, right? Then we go in this direction. But we see that this is branch 2, which goes opposite to the definition of cell 1. That's why we need a negative here. And we use the 13 points, which were employed to define this branch 1. And this is the common wall between cell 1 and cell 2. Okay? So that's this branch here. Okay? That's the number of the cell. In this case, it's cell 2. This is the branch 2. This is because it's negative. And in this branch 2, we considered all 5 points, which define this common wall between these two cells. Okay, And you can see that here, what it is, the program is doing is going to form, okay, the equation that he needed in order to calculate the Q1 and Q2, which are unknown, okay? So for each one of the cells, the program will calculate the Q1, which are constant and unknown, okay? And these are the results, okay? Here, with different colors, it shows the three branches that we're using. Branch 1 in yellow, branch 2 in magenta, and branch 3 in light blue, from here until here. And here, you have the shear stress distribution, right, in each one of the cells. Okay, remember, cell 1 started here and went downwards. So cell 1 is this one. So this part from here to here has 10 points. That's the distribution of the shear stress in the vertical longitudinal bulkhead in here. Then we have a jump in here. We have a linear distribution in the bottom, which is this one, from here until here. So about here, 4 meters from this here, about here, we see that the shear stress is null about here. And we have different signs. So since if we go like this, okay, this is the direction. Okay, so here, okay, we increase this distribution. So this is the larger value about here, neutral axis. Here we have a jump. Here we have a variation like this, okay? Here again, we have a variation. And this area is this part here. Okay, from here. Okay, and you see that in here, on the side, the stress value is minus 3.4. And in here, in the longitudinal bulkhead, the shear stress is about 4.5, I think, right? Because from here to here is 0.8. Yeah, it's 4.2, more or less. So the shear stress here is larger than here, okay? So that's the result of this calculation. Similarly for the other cell, right? The other cell starts here and you go like this. So this distribution from here to here, that's the distribution in here. Or it's negative. And this distribution on this side is equal to this one here because of symmetry. Okay? People, is there any questions about this process? Any questions about this process? You want me to say something or clarify something, people? Any questions? Did you try to use this program already, Ms. Valdez? Did you try to use this computer program to complete the assignment?
No yet, doctor.
Okay.
But today I'm starting.
Okay. Okay, good. Is there anybody who has already used this program to complete this assignment? No? Okay. Please start right away and try to include all of this information in a computer program, okay? Okay. Is there no more questions? Then I'm going to jump into the second part of the, is there a question? Is there a question, Mr. Guaman? Do you have any question? No? Okay. So let's go on now. Yeah, go on.
No, I don't have any question.
Okay, good. Okay, so I'm going to go now to the second part of the session, which is about the secondary stresses, okay? Start. Okay, so this is the content of this chapter. You see that we have already covered the first two parts. Now we have to say a couple of words about secondary behavior. Secondary behavior, you will see that we can run faster because there are many details which were basically reviewed in chapter 1. Because basically what we do is we convert this problem into a group of B problems, as simple as that. That gives us a nice approximation, okay? Okay, before we do that, in general, here we have a photograph or a figure to identify the secondary, what we consider a secondary structure, okay? Here, we have the hull of a ship, and you can identify this and this. What are these and that? Anybody? What's the name of these elements? What's this element here?
Transversal bulkhead.
Transversal what?
Double bottom?
No, come on. It's a bulkhead.
Okay.
Yeah, it's a
Bulkhead.
transverse bulkhead. Okay. You have to start used to the terminology, right? Because usually when you see the profile of the ship, they are clearly identified. So in many cases, they call it, for example, BLK. That's transverse bulkhead. So when you see in the profile, the XZ plan, you see as a vertical line. And there is a name here, BLK, meaning that's a transverse bulkhead, okay? And similarly, on the other limit of this compartment, we see another bulkhead. Now, in the upper part, in the deck area, we see the cross section, a cross area. That's what we consider a secondary structure. So it's composed, as you can see here, it's composed of plating. This is the deck plate, okay? This is plate. We have longitudinals, transversals. Okay, now you see that would you consider this as a longitudinal framing system or transfer framing system? Mr. Cedeño, Axel Cedeño, would you consider this as a longitudinal framing? Mr. Cedeño, Axel Cedeño?
Good morning, doctor. Yes, I think this is a longitudinal framing system.
Yeah, because you see that the longitudinals are very small and they are very closely spaced. Okay, that's the main characteristic. Now, we have to be aware that in this case, we have a strong and a strong longitudinal. Okay, these are side girders. And this, the maximum distance between these two is specified by the rule. I think it's 2.5. So if you have in this dimension more than 2.5, you have to include a strong longitudinal, even though it is a longitudinal framed system, right? In the transverse, you see that there is very strong transverse, okay, supporting the longitudinals, okay? Now here, he has decided that this is the transverse structure that he wants to analyze, because he considers that this and that are extremely stronger than the longitudinals. So this is what he's going to consider as the framing system. But if we had the tools, we could analyze all of these. Okay, so we could include deck plate, longitudinals, side girders, and side transversal girders also. So all of these would be our transfer structure. Now, the problem is that we need final element probably to analyze that, okay? And even in this case, we could take one single longitudinal, okay? This is a stiffener, okay? We add this piece of plate. This is the effective breadth, and we could consider this as a beam, as a single beam. We're going to consider that this is an extremely simple approach, okay? In this case, you consider that this is clamped here and here, okay? So instead of considering the whole thing, what you could do in a very simplified way, you could consider one single longitudinal stiffener, which is smaller. You could assume it as clamped here and here at part of the plate with the effectiveness, and calculate the inertia and calculate the response of this beam, okay? Now, this is a very simplified way. We try to see more like this one thing here, but of course, you have to consider that in this case, you have a group of beams that you have to solve simultaneously, okay? And of course, here, between longitudinals, you have a single plane. And this is what we call the tertiary behavior of the structure, okay? People, in this case, before we go on, in this case, okay, let's suppose that this is X direction and this is Y direction. In this plate, in what direction would be the largest normal stresses in the tertiary case, in the tertiary structure? In what direction would you expect larger normal stresses in the plate, in the X or in the Y direction? Mr. Pesantes, what do you say? X or Y in the plate? Mr. Pesantes, what would you expect? Larger stresses in the Y or in the X direction?
Good morning. And
remember, bending moments in general, in this case, since we are considering a deck plate, we can assume that the load will be uniform.
yeah, it's the
Okay.
Y direction.
A Y direction, yes. Remember, in this case, in case uniform load, the bending moments are larger in the direction of the shortest side. So that means that in this direction, in the Y direction, we're going to have larger bending moment than in this case. That means that in the Y direction, tertiary stresses will be important. We will review that next session, but it's important to start seeing the whole thing, okay? Now, you see that we will mention this in this session, that in the primary case, we would have a bending moment like this. And this would be M sub Y. This is primary bending moment. And this generates stresses in the X direction. And of course, in the longitudinals, we are going to have also stresses in the X direction, okay? So you see that these stresses will be combined with these stresses, okay? These stresses, tertiary, will be in the Y direction. They are not being to combine directly with the primary stresses because, yeah, these stresses are going to be there, yeah, but they are not that important as this one here. So you have to have all of these concepts in your mind in order to complete the last assignment. That's what I'm insisting, okay? Now, what we do in general is we take this secondary structure and analyze it, the word that I like is model. Okay, we see this in a simplified way as it were a group of beams. Okay, for example, in this case, I'm showing you two girders because you see that are stronger and two stiffeners. And you apply the load on all of them and you have to solve it. Now, if we think, or we remember, in chapter 1, we reviewed beam theory, okay? And what we have to do is we have to consider that in the points of connections, okay, there are some quantities which are common, okay? For example, you can assume that the girder is supporting the stiffener, right? So on the stiffener, the force will be upward. And the same force will be acting on the girder, but in the opposite direction. So that's a common quantity. And another common quantity is the deflection, right? The two, because of the load, will deform like that. So the deflection of this and the deflection of that will be the same. With these conditions, we will be able to apply simple beam theory in order to solve these type of problems, okay? Now, in general, in the P&A, that's Principle of Naval Architecture, that's it's a book by Snaney. In the volume 1, okay, volume 1 includes some chapters about structure. They mention that these are the four options that we usually have in order to analyze this secondary structure. Okay, one is the Kirilich theory, which is the one that we're going to be mostly using. So we take this, transform into a group of beams, and to calculate the inertia of each one of these beams, we include the effective breadth of the plate. Remember that we have this problem is different than this one, so the effectiveness of the plates in one and in the other direction could be different, okay? So that's the first thing that we have to do. Now, in here, please pay attention to this. They're supposed to have two stiffeners like this, okay? And because of the load, the two will deform, but the two probably will deform like this. One will deform more than this one here. So we go like this, but these deform a little bit more. So they tend to rotate. That means that this action should be considered in our analysis. And that action is the torsion. Okay, so when you see the plate deform like this. So any stiffener will be rotate a little bit. So we should include the torsion in the analysis. And, in certain cases, it could include some importance. But in general, we could simplify and say, okay, forget about that. We are going to consider only bending, not torsion. Okay? But you have to have that in mind. The second theory mentioned by the P&A is the theory of beams under elastic foundation. Okay? There is a very nice article on that in the 70s, some 50 years ago. And a graduate from the University of Michigan, he applied Laplace transform. And in order to convert a differential equation, because the Laplace transform of the delta Dirac function, see, when you have concentrated forces, you can represent it using delta Dirac, but the Laplace transform of that is finite, so it's easy to handle. Okay, so that's what he employed. Then we have autotropic plate theory. Okay, so for example, you have in one direction you have several stiffeners, and in the other direction you have girders, but the height, the inertia of this is different than the inertia of this. So what orthotropic plate theory is, takes this this difference, okay, the stiffeners and the girders, and calculates some sort of average bending stiffness. Remember that the plate bending stiffness what letter do we use in order to specify the plate stiffness? Anybody? Mr. Chin Chin, do you remember what letter we use in order to specify the plate stiffness? Mr. Chin Chin? What letter do we use? Mr. Chin Chin?
Um,
Come on. You forgot.
no, doctor, I don't remember.
Tremendous. Do you remember what letter we use in order to specify the plate stiffness or plate rigidity? Plate rigidity?
No, doctor, I don't remember that.
Mr. Yangare? Mr. Yangare, do you remember what letter?
Is D?
D. How do you find D, Mr. Yangare? Do you remember how do you find D?
Yes, is Young modulus by thickness to cube
Okay, to the third power divided by?
over 12 by
Okay.
1 minus Poisson ratio to square.
Yeah. Okay. We insisted in chapter 4 that this is something that we have to keep in our mind. Okay. There are some relations. Yeah, you can look it up in the tables, but this is something that we have to keep in our mind when we study plate theory. Well, in the case of orthotropic plate theory, we have two values of D, one for the X and one for the Y direction. Why? Because in one direction, we have a stiffener, which are small. And in the other direction, we have very large girders, which are much stronger. So what we set up is an equation which have two values, dx, dy. And also, there is another term which reflects the influence of the torsion. So it's very similar to the case of chapter 4, but the equation is a little bit more complicated, okay? And that's the theory which was applied by engineer Ahila, Karina Ahila, in her thesis, okay? And finally, this is something that we're going to be using next semester, right? We have this plate with stiffeners. What we can do is we can partition, okay, this structure. And we can represent that with little rectangles. And each one of these little rectangles has to be defined with 4 joints, right? So this one here has 1, 2, 3, and 4 on. There's another adjacent, 1, 2, 3, 4. And the two have 2 joints in common. So they are connected. And this is what we do when we apply finite elements. Yeah, this is much, much more precise, of course, but the problem with that is that you have to spend a lot of time in order to develop the model. Once you get to the model, it's easy, or relatively easy. The last part of the analysis, you have to take a lot of information and you have to analyze. That's something that we usually sometimes try to avoid, but no, it's our responsibility as engineers, okay? So from these 4, mostly what we're going to talk about is the grillage theory. And at the end of this session, I will mention one extreme case, okay? That is this one here. Basically, in a very simplistic, okay, but of course that might include some error, but in a very simplistic way, what we can do is we consider that one single stiffener is well clamped on both ends on girders. So we consider it simply as one beam, okay? But that's very simplistic, okay? So we're going to consider that as an extreme. But mostly we're going to be working with grillage theory, but simple cases, because it's a long process, okay? We have mentioned several times that this plate here is welded to this stiffener in general. But the distribution of normal stress will be something like that because of the influence of the shear. That's something that we have studied in chapter 2, okay? So at the end, we're going to have something like this. Okay, so in order to estimate the maximum normal stress, what we do is we define an equivalent normal stress distribution with uniform maximum value for the normal stress. But since this increases, you see that here I have a lower than the maximum. Since you are considering this is uniform, you are increasing the force. So what you do is you reduce, instead of B, you reduce the width of the flange. Okay, that means that BE is a little bit smaller than B. Okay, and this ratio, BE over B, is what we call the effectiveness of the plating. Okay, for example, somebody can tell you, okay, do this calculation and use 80% as the effectiveness of the plate. That means that you take B, multiply by 0.8, so you reduce it, and with that, you go on and calculate the inertia. Okay, that allows you to estimate the maximum value of the normal stress on the plate, which is this value here. Okay, now, we have to be careful because in this case, we are working with bending. Okay, that's what we call the effective breadth. In this case, we could also apply a column loading, see, axial loading. And in that case, the concept is similar. It's not the same, it's similar. And in that case, we call it effective width. Okay. For example, in some cases, okay, when you have a primary stress, okay, say you have compression on the deck, okay, and the compression on the deck may cause buckling of the longitudinals. Okay, so what you have to do, is you have to calculate the inertia and calculate the critical stress of the longitudinals. And for that, you have to add the effective width. Okay, so in that case, you use effective width. Okay, so here you have the two versions. Okay, it's a combination of the two. You have this line. This is for column buckling. That means that you are talking about effective width. And the continuous line is for beam loading. That's the effective breadth that we use when we consider bending. Okay, so we have to have that in our mind. Now, most of this work is the result of contribution from Professor Shady. Maybe you remember this name from chapter 2. Okay, here, does anybody remember what KL means? KL? Mr. Tenemea, do you remember what KL is? What KL? Mr. Tenemea? KL?
The effective breadth is?
No. KL here. KL. Mr. Yomero, Jandri, do you remember what KL is? KL?
I don't remember.
You don't remember? Anybody remember, please?
Say.
Mr. Jangare, do you remember?
Yes, is letter A.
Yeah, but what it is? It's the distance between points of zero bending moment. Okay, remember now? So you consider the loading, consider the boundary conditions, you draw the bending moment distribution. So you check the distance between points of zero bending moment, and that's your KL. K is a percentage. For example, in the case of simply supported, you have zero bending moment on the ends. So you have a distribution of bending moment. So in that case, K is equal to 1. Okay? Chapter 2. Okay, so that's the concept of, how can I say, it's from the source, the concept of effective breadth. But in our case, we could apply more modern information. Okay, for example, this is something that we have already employed. For example, the rules from DNV, okay? In the case of girders, okay, strong elements, they are welded to the plate. They have to consider, of course, the girders, they support in general to the stiffeners. So if one stiffener fails, yeah, but you still have the plate and connecting to the girder. If one girder fails, we're in trouble, because usually there is a region in the secondary structure that probably is going to fail. So in the case of the girder, you have to be very careful with the selection of the effective breadth. Okay, and this table, remember, was presented by DNV. And in this case, you take the value of C from this table and you put it into here, and that's the effective breadth that you have to apply. Okay, in this case, okay, A over B, remember, here, A is the distance between zero bending moment. And B, of course, is the spacing between girders, or that's the width of the plate, which is welded to the girder. Okay, so B here, total width of we have insisted that every reference has different terminology. Remember, when we studied this problem in chapter 2, Professor Shady used little b and large b. And for the spacing between point of zero bending moment, he used KL. In this case, DNV uses A for the distance between point of zero bending moment, and little b uses for the total. See, you see here, I insisted in this objective. Okay, it's total. You see here, from here to here. So we have to be careful when using different references. Okay, before using that, you try to see, okay, what's the meaning of this letter in this term in this reference. Okay, so don't assume that they coincide. They usually do not coincide. Okay, and R, does anybody remember what R is? Anybody remember what R is?
The number of stiffeners.
Exactly, number of stiffeners. Okay, when R is larger than 6, that means that you have a large number of stiffeners, and probably this is very close with the assumption made by Shady. When you have, for example, little number of stiffeners, okay, this is the girder, you have these stiffeners, okay. It's different. If you have very large number of stiffeners, you can assume that on the girder, you have uniform loading. But you have a low number of stiffeners, it's very difficult to do that assumption. Okay, that's the general the meaning or the message behind this. Once you have that, you get C. With C, you multiply by B, okay? With C, you multiply by B, and you have the effective breadth. With effective breadth, you go on and calculate the inertia. And with inertia, we could apply Grillage theory in order to analyze this as a group of beams in the two directions. In one of the first assignments that I gave you, I asked you to analyze this type of situation, right? We have two beams like this. Because, see, I foresee that we needed this for this situation. Is there any questions about these people before we go to the break?
Yes, doctor. How we
analyze to convert the inertia of the blade of the girder to the simple girder.
Would you repeat that, please? I didn't get it.
So you said that we have to convert the inertia of the plate with
No,
the,
we don't have to compare. We have to calculate. We have to calculate.
just just the girder alone or the girder with the plate. We have to convert in a
No, you're
I mean-
mixing. You're mixing terms here.
yeah.
So let's suppose I have, this is B. Here I have the girder. What I do is I calculate, I get A, I got R, and with B, we determine C. With C, I calculate B sub E. And now what I do is, okay, instead of having this is B, okay? Instead of that, what I do is I take only one piece of that. And then I calculate the inertia, and finally, sigma secondary.
Okay, I thought that it was converted again to the like a beam.
Mhm. Yeah, after we calculated, because we are considering secondary structure. Secondary structure, we model, okay? We model the combination of plate plus stiffeners, okay? We convert this into something like this. This is the idea behind grillage theory. And
Okay, then
so each one of these has a little piece of the plating forming its flange. How much? That's the effective breadth. With the effective breadth, we calculate the inertia of the girders. We do something similar for the stiffeners. In general, the two effectiveness are different in general. So we have to do two calculations, effective breadth for this, effective breadth for that, inertia for this, inertia for that, and now we're ready.
okay. Thank you.
No problem. Okay, let's take a break, 5-minute break, and when we return, we will go on with the calculation of the combination of the two beams in orthogonal directions using simple beam theory.